Hello, my name is Ben Klukshesky. This is Lab 4 Circuits, Physics 2212. Alright, for the contents of this presentation. First up, we'll have the introduction, which will be the description of the lab and the fundamentals. Second of all, we'll have observations, data, calculations, which will be setups, results, and analysis. And finally, we'll have a few final questions and a few final thoughts on the matter. Alright, introduction. So the goal of this experiment is to observe, analyze, the behavior of circuits, capacitors, and resistors to gain an understanding of how they work. Alright, in this experiment, we used a few formulas and principles. First up is Kirchhoff's loop rule, which states that the summation of voltage across the entire loop must be zero. Second of all, we have the node rule, which states that the sum of current entering the node is equal to the sum exiting. Finally, we have Ohm's law, which simply states that voltage equals current times resistance. Alright, first up, we simulated a simple circuit with two 1.5 volt batteries, 2 ammeters, and 2 resistors. One resistor at 47 ohms and the second at 100. First of all, what do you predict that current 1 and current 2 would be? Using Ohm's law, I predicted that they'd be approximately 0.0204 amps each. And was the prediction correct? Yes, it turned out to be correct, as both ammeters read approximately 0.02 amps. Next up, we did a variation of the previous simulated circuit, but this time we replaced one ammeter with a voltmeter. As you can see in the table, we plotted voltage at different points in the circuit, and you can see the listed voltages on the right. Now, what were the values after replacing the ammeter with a voltmeter? Current is now 0 amps, and voltage is now 3 volts. Now, why? This is because the current equals 0 because the loop is broken. Using Kirchhoff's loop rule, we can verify the summation of the voltage does equal 0 by summing the right values on the right side of the table. Total, they equal 0. Alright, here's a graph of the voltage across that simulated circuit, and as you can see, we go up to 3 volts at one point, and then each drop-off is due to a resistor. The current and voltage encounters resistance, and voltage drops off as a result, ending at 0 volts. A few questions. Why doesn't the ammeter reading change after attaching the voltmeter? That's because the infinite resistance provided by the voltmeter means the current can't pass through the voltmeter. What was the reading of the ammeter after connecting the voltmeter? It remains 0.02 amps. And what happens if the voltmeter is replaced with an ammeter in parallel? They're roughly tripled, meaning they go up to 0.06 amps, and that's because ammeters have zero resistance. As such, the current now flows through the ammeter path instead of the path with the 100 ohm resistor. Calculations are on the right. Alright, setting up the final circuit, we had a 9 volt battery, a capacitor, and a 30 ohm light bulb. Procedure was to measure and discharge the voltage of the capacitor, and the data we recorded and plotted 20 seconds of data from the circuit. This is what we observed over time of the voltage and the voltage over time. As you can see, it follows a fairly linear path of regression. Now, the what ifs and whys. So what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What would be different about the real ammeter? The answer to this is that a real ammeter would contain at least a minimal amount of resistance, which would affect the values measured in the experiment. Instead, the one we used was theoretical, of course, it was online, and that contained zero resistance. Now, what if you're doing this lab in real life and used a real battery to charge the real capacitor with no resistor in the circuit? The capacitor would charge almost instantly, however, not exactly instantly. There'd be still minimal amounts of resistance with the circuit, like the wires. But again, charge almost instantly because of the lack of resistance, because this resistor was removed. Right, that's it. Thank you.